careful. I don't even know how you're texting me if you're driving. Where am I? Okay, let's get started. Let me know when you can see. Oh, okay. Can y'all see the screen?
Yeah.
All right. Okay, today's actually going to be fun. I'm so excited. Get your, this is one of my favorite sections to teach. Get your calculators ready, but I'm going to be using Desmos a lot because y'all can't see my calculator in front of me. So I'll be using Desmos to show it to you. Yesterday, we ended with reviewing what it means for a graph to be symmetric. We reviewed even and odd, being symmetric about the y and the x-axis. And the reason why I wanted to go over that is because that polar graphs can also be symmetric, okay? So I think we kind of went over how we determined if something was even or odd. So we are at the bottom of page 106, and these are the tests for symmetry when we're trying to figure out test for symmetry for specifically polar equations. Okay, so let's just look at the rules first, and then we'll actually try some examples. I would get additional paper. There is not enough space at all in this section, which I've already flagged. I'm going to tell them to put more space in it. So if you need like a second to get some scratch paper or maybe like your spiral, because there's no way any of this is going to fit. So you want to make sure to get that. Okay, so let's say that we want to see if you are symmetric about the polar axis. Now remember, between you and I, the polar axis is the same thing as the x-axis, except polar axis is in polar form, and of course the x-axis is in rectangular form. So same thing. So if we wanted to see if you are symmetric, if the graph is going to be symmetric about the polar axis, we are going to replace theta with negative theta, and it should come out exactly the same. So if we put in negative theta, simplify, and it comes out exactly the same, then we're going to say, yep, it's symmetric about the polar axis. Okay. Number two, let's say I want to figure out if we're symmetric about the pole. Again, if we're comparing this to rectangular form, remember the pole is the same thing as the origin. Okay. So if we're going to do that, what we're going to do is we're going to substitute in theta plus pi. And if you get the same thing back out, then the answer is yes, you're symmetric about the origin. Okay. And then last but not least, what if I want to figure out if we're symmetric about theta equals pi over 2? Comparing that to the rectangular plane, it's the same thing as the y-axis. And what we're going to do here is we're going to substitute pi minus theta. We're going to simplify. And if we get the same thing back out, then it is symmetric about the theta equals pi halves. Is everybody cool with the rules? I basically just summarized the bottom of page 106. Sure. It's the same thing on the bottom of page 106. Okay. So we're going to do example 1, but like I said, there's no way this is going to fit. I don't care if you write super small. There's no way that's going to fit there. So I really feel like that whole picture should be on the next page and we should have all of that space. So I'm literally probably going to use a whole page per problem, to tell you the truth. Okay. Okay. Let's come down just a tad. So the first example we're going to look at, which is A, is R equals 4 minus 6 cosine of theta. So R equals 4 minus 6 cosine theta. This is a polar equation, and if you read the instructions, it wants us to test symmetry with respect to the polar axis and the line theta equals pi over 2. So I have to do all 3 tests. Is that cool? So we're going to do one at a time. The first one I want to do, and it doesn't say in any specific order, so I'm just going to go from test to test. The first one I'm going to do is I'm going to see if this is symmetric about the polar axis. So I'm going to do the polar axis first. Now, if you remember, going back up here, the polar axis, what we're going to do is we're going to substitute in negative theta. Okay, so I'm going to find R of negative theta. That's the rule. So if I come over here and do that, wouldn't I get R equals 4 minus 6 cosine of negative theta? And now I'm going to simplify this. What can you tell me about cosine and having a negative angle inside of it? Do y'all remember? How come I can just switch this back to cosine of theta? Anybody? Thank you, Georgia. Remember, cosine and secant are the only trig functions that are even. So if you have cosine of negative theta, you can just rewrite it as cosine of theta. You could just drop the negative inside of the angle because it's even. Cosine is even. So I simplified. If you look at what I have now and you look at what I started with, they are the same. I don't know if I could write sideways on this thing. Yeah, I can. Okay. They are the same. And since they are the same, yes, it is symmetric about the polar axis. And that's the polar axis test. Is everybody okay with that so far? Any questions? Moving right along. Yeah. That's it for polar axis. No, we're not done with A. You have to do all 3 tests. We only did 1 test. So the next test I'm going to do is the pole. Let's do the pole. Okay, so I'm going to do the pole test. If you come up here to the rules, to do the pole test, I'm going to replace theta with theta plus pi. So I'm going to have R of theta plus pi If I do that, I would have r equals 4 minus 6 cosine of theta plus pi. We okay so far? Any questions? No. I am not just adding pi to do anything. That's the test. Like, this specifically says, if you are trying to test for the pole, you are going to replace theta with theta plus pi all the time. Then we're going to simplify to see if it is the same. We're not trying to make sure it's the same. We don't know if it's going to be the same or not. But if it is the same, then it's symmetric about the pole. If it's not the same, then it's not symmetric about the pole. And that's it. That make sense? And so now I'm going to come over here and I have to simplify this to see if it is the same, right? We're always going to compare it back to the original problem. This is the original problem. So is this, what we have here, the same thing as the original problem? Well, let's see. We have to simplify it. So I'm going to get r equals 4 minus 6 times, oh my gosh, what is it? Cosine of theta cosine of pi minus sine of theta sine of pi, right? Garrett? Oh, I got these wrong.
Yeah, that's right.
Okay, cool. Oh. Are we okay with these? With my replacement? Now, what is sine of pi? Isn't sine of pi 0? So this is gone. So then this just simplifies to cosine of theta. What is cosine of pi? Cosine of pi is -1. So this would give me 4 plus 6 cosine theta. I'm stopping. Yep. Yeah. 0 times anything is 0. So, it's gone. We okay? Now that I simplified this, is this the same thing as the original problem? This is not symmetric about the pole. Is that okay? Any questions? Moving right along. We have one more test. We have to test the line theta equals pi halves, which remember is the same thing as the y-axis. And if we go back up here to the rule says we're going to replace theta with pi minus theta, right? So the test is I'm going to replace theta with pi minus theta. If I do that, I'm going to have r equals 4 minus 6 cosine of pi minus theta. Yes, no, maybe? So if I were to simplify this, I would get r equals 4 minus 6, bracket, cosine pi cosine theta, plus sine pi sine theta, right? Sine of pi is still 0. That's gone. Cosine of pi is still -1. So this would give me so this is not symmetric about theta equals pi halves. And that is one problem. That is doing 3 tests of symmetry for one graph. You see how I say that's not enough space? This is all part A. Any questions? Yes, no, maybe?
Will it always only be symmetric about one axis, or can it be multiple?
I'm trying to think. No, I know. I think you can be symmetric. You know, for sure you can be symmetric about more than one. I'm trying to think like of a good example of one, but you can be. So you have to test them all. For sure. Because roses can be, you'll see roses later, but roses can be symmetric about all 3. Is everybody okay with the test though and how to do it? Yes, no, maybe?
Yeah, it kind of makes sense.
Okay. Let's do another one. So the next one we're going to do is B. Okay. And do you agree that B says R equals 3 cosine of theta cosecant of theta, which can be written as 3 cosine of theta over sine of theta? Because I know the rules for cosine and sine. I don't know the rules for cosecant. Is that okay? So then, now that I have this, then we can go ahead and start testing. So the first one I want to do is the polar axis. Right? And remember, with a polar axis, you're going to substitute in negative. It's supposed to be negative. I was doing my theta sign outside of it. Are we okay with that? We're going to substitute in negative theta, and then we're going to simplify it. So if I were to substitute in negative theta, wouldn't I have 3 negative theta? Ugh, what was wrong with me today? Sorry. 3 cosine of negative theta over sine of negative theta. Everybody good with that? And then cosine of negative theta would simplify to what? Okay. So I dropped the negative sign inside of the cosine, and you can do that because it's even. But notice what I did with sine. I took the theta, the negative, inside with the theta, and I had to put it up front because sine is odd. Write that down if you forgot. So sine is odd, which means that negative sign has to come up front. So now if I simplify this, the whole thing's negative. So that would give me negative 3 cosine theta cosecant theta, which is not the same thing as the original problem. So therefore, this is not symmetric about the polar axis. Any questions? Yes, no, maybe? Okay. Let's do the pole next. The pole, for the test for the pole, is we are going to replace theta with theta plus pi. Do you agree with that? So I would have r equals 3 cosine of theta plus pi divided by sine of theta plus pi. So go expand the numerator, expand the denominator, and then we'll see what we can do as far as simplifying. Is everybody okay? Y'all are super quiet. Any questions? No, yes, maybe. What you'll start to notice is that we already did this. Didn't we do 3 cosine of theta plus pi a minute ago? Didn't we? And that came out to negative cosine theta. So I would get a negative. Do you want me just to do it, or am I don't shortcut or shortcut? Yep, I can. So this would be 3 times cosine of theta cosine of pi, right? Minus sine of theta sine of pi all over. My wife is an important meeting, so I won't be able to talk for a bit. Oh, it's okay. It's okay. Please put in the chat though if you have any questions. Okay. Okay. On bottom, we will have, what will we have on bottom? I don't remember. Anybody want to do it? Did I do it wrong? Because that's the formula? Did I do it? Remember, I was getting these wrong last time, and Garrett kept correcting me because I was putting them wrong. Like this one is sine of theta, sine of theta, sine of pi, sine of theta, sine of pi. No, I'm lying. I'm lying. See, I'm already doing this wrong. I can never do this. Sine of theta, cosine pi, right? Plus addition and subtraction problems that we learned back in chapter 7 when we were adding 2 different angles. I think it was like section 7.2-ish. It was at the beginning of 7. So sine of theta cosine pi, cosine theta sine of pi. Is that okay? So then if I were to simplify this, this is gone because sine of pi is 0. This is gone, sine of pi is 0, right? And so then cosine of pi is -1. So on top, we get -3 cosine theta. On bottom, I get cosine of pi is -1. I get negative sine of theta. which comes out to 3 cosine theta sine theta, which is exactly that. So this is symmetric about the pole. Page 83, I found it. Page 83. Top of page 83 is where I'm getting these addition problems, addition and subtraction formulas, just in case you're looking. Are we okay with that one? Any questions? Ooh, okay. I'm gonna make this one the last one. We're spending too much time on this. So this is theta equals pi over 2, right? And remember, when you're doing pi over 2, you're gonna substitute in pi minus theta. That should be a lowercase r. I don't know why I made it there. Go back up to the test. Oh, in case it's done. If we're doing theta equals pi over 2, which is the y-axis, we're going to replace theta with pi minus theta. So we're going to replace this with pi minus theta, and then we're going to see if we get the same thing back out. So in this case, I'm going to have r equals 3 cosine. So r equals 3 cosine of pi minus theta over sine of pi minus theta. So then again, if you go look at the formulas on page 83 that helps us expand these, are we okay? We get on top 3 times cosine pi cosine theta plus sine pi sine theta. That's the numerator. Yep, okay. And then in the denominator, we get sine pi cosine theta minus sine theta cosine pi. Theta cosine minus. Yep, okay. Sine of pi is 0, sine of pi is 0. So in the numerator, I get negative 3 cosine theta. The denominator, I get a positive sine of theta, right? That is not the same thing, and so therefore it is not symmetric. Are we okay? Above it? Okay, cool, because I don't know where you are. I'm lost in the sauce over here. Are we okay? Any questions? Super quiet? Okay. Okay, I'm gonna skip C because I feel like we just spent 30 minutes on 2 problems. So I'm gonna skip C, but literally we would do the same thing, okay? We would do the same thing. You would substitute in negative theta, you would substitute in theta plus pi and pi minus theta into there, simplify, see if you get the same thing back out, and that's how you'll determine whether it is symmetric about whatever you're testing. Okay. So there are common polar graphs. There's common polar graphs that you can graph. Just like in the rectangular plane, you have different functions that if I told you what they are, you should have a good mental image of what it is. A quadratic function, oh, that's a parabola. A cubic function, oh, that looks like an S, right? A square root function. So you have these different functions that you should have a good representation in your head of what it looks like. It's the same thing on the polar plane. So here are the common types of polar graphs. The first one is a limicon. So if you look at it, it kind of has like this, you see them? They're down there. So you have this limicon with a loop. And if you look at it, it has this loop. That's the first graph. Then you have a cardioid, and we're not that creative. We call it a cardioid because it looks like a heart. And then we have a dimpulse limicon because it's not really a big indention. And then you have a convex limicon. So those are the pictures there and the formulas for limicons. Is that okay? So let's actually draw them. Oh my God, please don't make me, Garrett. This is it's fun to draw it, but I've never done this lecture like this before. And I'm literally have anxiety. Like, I don't even know what I'm gonna do. Okay, so the first one is r equals 3 minus 5 sine theta. So do you have your calculator? Remember, to be in polar form. So get into polar form. 3 minus 5 sine theta, okay? And so this can really help. This can really help with what we were just doing. So we're going to have 3 minus 5 sine theta. What I'm going to do is, if you have put it into polar form, put this in there. I'm going to graph it on Desmos so we can all see it together, okay? So please let me know when you see my screen. Does everybody see Desmos okay? Y'all talk to me because I can't see your chat now that I'm doing this. I'm sorry? Can y'all see my screen now?
No, ma'am.
Perfect. Thank you. Yeah, keep talking to me because I don't know what you can see and what you can't. So I just want to make sure. I know what I'm allowing you to see, but it won't tell me. It won't tell me when you see it. Okay, so I'm in Desmos, and I'm literally going to start typing r equals 3 minus 5. And then I'm going to do sine, and I'm going to start typing theta. And notice how it turns into a theta. And here is the picture that you should see. How cool is that? Do you see this on your calculator? Make sure you're in polar form, 3 minus 5 sine theta. And I would start with a standard screen, like a standard window. And it should graph it. I'm looking on my TI and I see the same picture. Are we okay? Any questions? What numbers? Page 108, we're on the next example. Is everybody okay? Mine looks on my TI looks a little bit more eggy, but You get the point. You get the same picture. The point is on your homework, this is such a fun homework because on your homework, I'm just going to have 4 graphs and say, hey, which one's the right graph? Does it make sense? And you should be able to identify that this is a lemicon with a loop. Do y'all see that? So I want you to write that on your paper. Can you see my paper now too? So we know that this is a lemicon with a loop, with an inner loop. You should be able to sketch it. Is that okay? And you'll be able to pick it on your homework. And then it's asking for symmetry. So let's look at this. How is this symmetric? Remember, this is the polar axis, the horizontal, the x-axis. Is that x-axis cutting this bad boy in half? Where there's symmetry? No. Okay, so maybe the y-axis is where you have symmetry. So this cuts my workload in half. I'm going to come over here and test y equals pi halves. I'm only going to test that one because remember before we were testing all 3 and we were testing all 3 because we didn't know what it looked like. So we had to test all 3. But now that you have a picture, I can see that this is not symmetric about the polar axis. I can see that this is not symmetric about the pole, but I'm pretty sure it's symmetric about the line pi halves, but you still have to prove it. So then you would come over here, and remember, in order to test if it's symmetric about pi halves, what do you have to substitute in? Anybody remember? We're just learning this today, so it's okay. But for theta equals pi halves, you're going to substitute in pi minus theta. Is that cool? So I'm going to come over here. R equals 3 minus 5 sine of pi minus theta. And so I'm going to have 3 minus 5, open bracket, isn't the formula sine of pi cosine theta minus cosine pi sine theta. I got this from page 83 of us expanding these. Sine of pi is 0. That's gone. Do you agree with that? And so then I have 3 minus 5. Inside, I have negative 1 times sine of theta. If you distribute that negative 5, I messed up somewhere. Where did I mess up? Oh, this would be a positive 1. Sorry, because you have a negative 1. There we go. So that's be a positive 1. So now if you distribute the negative 5, you get 3 minus 5 sine of theta, which is exactly what we started with. So you just proved that this is symmetric about pi halves. Does that make sense? So where it says symmetry on your workbook, you should be theta equals pi over 2, but you right under it, I gave you a little bit of space for you to prove to me that it's symmetric about that pi halves. And so you would put that there. And then you have a little graph on the side where you should be sketching the graph. Is everybody okay with how to do example 2? Any questions? We're okay? Okay. So let's do another one. The next type of graph, so those are lemicons. The next type of graph that we're going to do are roses, okay? And with roses, the number in front of your theta will tell you how many petals it's going to have, like even or odd amount of petals. So for example, n petals when n is odd and 2 n petals when n is even. Okay, so it'll make more sense when we do it. So let's look at example 3. I want you to try to graph it in your calculator. So for example 3, it says r equals 5 cosine of 4 theta. So 4 is even. Do you agree with that? The number in front of your theta is even. So if you have an even number, right, that means you're going to have double the amount of petals. So I'm expecting this to have 8 petals. Go graph it and let's sketch this bad boy. I'm going to go to Desmos. Look how pretty. Did you get this on your graph? Any questions? Are y'all there? Can y'all see my screen? Testing, testing. Okay, let's see. Okay, good. Okay, just making sure. How cool is that? This would be super hard to graph on a rectangular plane. Does that make sense? Super hard to graph on a rectangular plane. Now, my question to you is, where do you think this has symmetry? Garrett, going back to the question that you had earlier, where do we think this has symmetry? Y'all are going to hate the answer. Anybody? Yes. Good job, Garrett. All 3. This looks like all 3 of them. That it's symmetric about the pole. And let me just give you a, maybe this will help. Okay. Let's do black. I want to be super. Okay. Look up here. So doesn't the, I'm going to try to be as straight as I can. Doesn't the y-axis cut this bad boy in half? Can y'all see me cutting this in half? So if you were to fold it about the y-axis, it's symmetric on both sides. The x-axis, isn't the x-axis cutting this in half? If you were to fold it along the x-axis, they would be the same on both sides. In order to be symmetric about the pole, remember, that means that if you were to turn this 180 degrees, if you were to turn this upside down, would it be the same picture? And the answer is yes, it would be the same picture. And so therefore it's symmetric about the origin as well. That makes sense? So I'm pretty confident it's symmetric about all 3, but what you want to do is you want to make sure that you're proving it as well. Okay, you want to get that practice. So I would practice this, but yeah, it's symmetric about all 3. So you would put all 3 answers. Is everybody okay with the roses? Now, does that mean every single time that roses are going to be symmetric about all 3? No, it depends on how many petals there are. Does it make sense? Any questions?
So like
I'm sorry?
even petals will be symmetric around all 3 just about every time, but odd will
Yeah.
only.
But odd, no.
Yeah.
I don't, because I'm looking at the third picture. If you look at the rose curves, look at the third picture where you have 5 petals. I see that to be symmetric about the line pi halves, so the y-axis, but it is not symmetric about the origin. It is not symmetric about the x-axis. Do you see that?
It wouldn't
So
be
it's
symmetric of the origin? If you rotated that 180 degrees,
180
it wouldn't be the
degrees?
same?
No, because if you did it 180
Oh, no,
degrees,
it wouldn't.
you would have this loop
No,
on
no.
bottom,
Yep.
right? So yeah, and so, but Garrett, what you just did, if you're like, hey, would that be symmetric about the origin? If you're thinking about it, test it. Does that make
Gotcha.
sense? Do the
Yes,
test.
ma'am.
Like you're like, oh, it looks like it might be. Well, do the test to confirm it. So that's exactly what it is. And think about this. Think about the words that I'm using, you guys. This is exactly what's happening right now, especially if you want to be a doctor. It looks like corona. Well, shoot, let's test it. Let's test to see if it is. Do you see what I'm saying? They have all the symptoms of it, but you still have a test to back up what you think. So that's exactly what we're doing. We think it's symmetric about this. We'll then test it to confirm. Cool? So those are Rose curves. Okay, so we did that one. Page 109 is the last graph. We're going to do circles and lemon skates. Do y'all see them? Okay.
Yes, ma'am.
So of course you have these circles. If it's cosine, it's probably going to be around the x-axis. If you notice how if you use sine, it's more centered around the y-axis. And then lemon skates are like these infinity signs, okay? So the first one on the left, we have -4 sine theta. So if you put that into your calculator, -4 sine theta, you get this lovely picture.
It's literally just kind of like a vertical shift across the y-axis for the circle.
That makes sense. And then if you did -6 cosine theta, you would get it on the negative side. Does that make sense? You would get it on this side because it's negative and it's cosine. If you change that 6 to a +6, notice how it just flips over to the other side. Do y'all see that? Cool, huh? And then you can test symmetry. How are we feeling? Are we okay with this? Y'all are gonna love this. Homework is a lot of just graphing it and then matching up the graphs. So as long as you're comfortable putting this in your calculator and identifying these graphs, it's good. Some of them are gonna ask you where you're symmetric. Okay, so I taught you all 3 tests today to figure out where it's symmetric. So you'll be able to practice that. But I do want to go to page 110 because 110, I have an application problem there for us to do, but I also want to add an additional example. So make sure that you're leaving some space at the bottom to do an additional example. So example 5 says, the orbit described in exercise 63, and I wanted to go over this with you because you don't see exercise 63. So is stable because the satellite traverses the same path over and over. So satellites right now on Earth, they travel around Earth, these satellites, in the same orbit. They travel around the same orbit every single time. But what happens if this satellite gets hit by a meteor or something like that, or gets hit by something? Then it's going to get off of orbit and eventually it could hit Earth. The thing with the satellites is that the way that they're designed is that if it does try to fall to Earth, it doesn't matter. It's probably going to disintegrate in our atmosphere anyway. Does that make sense? So it's okay, but we just lost the satellite. So with this one, the one that we're going to look at now, we're going to have an unstable orbit. So if you look at part A, it says on the same viewing screen, I want you to graph a circle, r equals 3,960. So if you come over here, I'm going to graph r equals 3,960. Oh, no, I'm not. Equals 3,960. Okay. If you notice, you can't see anything because it is definitely too small. So there it is. Now, if you are wondering the significance of 3,960, that's how many miles the radius of the Earth is. So this is a good representation of our Earth. Is that okay? So if you put this in your calculator, you will be able to see it, but you're going to have to fix your window. So if you go, I'm going back to the Word document. Can you see the Word document okay? I had to fix my window, and you'll see if you go to window that you have these new options. My theta min is going to be 0. My theta max is going to be 3 pi. And the reason I made it 3 pi is because if you read part A, it says with theta increasing from 0 to 3 pi. So that I didn't make that up. They told me 0 to 3 pi. 0 step, okay, is something that you might want to play with. But the reason you have 0 step is how many tick marks it's going to have. Like, what do you want me to count by? The smaller that your step is, I would say the better it is because you're going to have tick marks every single time. I tried pi 6, but it came out kind of eggy. looking more than it did round. So I went over here and made it a bit smaller, pi 12th, and it came out to a really pretty circle. So you might have to play with your step a little bit just to see if you get a good picture. And so then for my X-min, I did negative 8,000. My X max, and this was me literally playing with my window, was 8,000, and I counted by 500. And then my Y min, I did the same thing. My Y min, negative 8,000. My Y max, 8,000. And then my Y scale, I got 500. And when I put, this is for my calculator. When I put this in my calculator, I was able to see everything. Now, on your homework, if you get something like that, you might, like I said, you might have to play around with your window a little bit so that you can see what's going on. But this helped with this problem.
Is there a shortcut to reset all this back to the regular settings?
What kind of calculator do you have?
TI-84.
Okay, yeah, Zoom 6. So when you're on your graph, that's it. If you have a TI-8384, if you hit Zoom 6, you'll go back to a standard window when you're graphing.
Oh, cool.
But now you can't see anything because it's too small, right? But so you'll want to fix it, but then you'll go back to Zoom 6 it. Okay.
Okay, cool. Thank you.
So I just wanted to show you what I did with my calculator because I don't want you to email me and say, I can't see anything. It's because your window's too small. Okay. So here's this. The next equation I'm going to put in is the one for the orbit of the satellite. So I'm going to have R equals 22500, 1 minus theta. Ooh, it's not even 1 minus theta divided by 40. Close, close. Divide that by 4 minus cosine of theta. And I want you to look how many times, do you see the green picture? The green picture is the satellite, but look at over here at R. This is going from 0 to 12 pi. So I'm letting it go around and around and around the Earth. Does it make sense? A whole bunch of times. I'm going to restrict it. I only want it to go around the Earth 3 pi times. Make sense? So it's starting here. Over here, do you see where my mouse is? It's starting at 8,000. Remember, it always starts at the positive x-axis. And then it went around. At first, it cleared it. We cleared Earth. If you want to zoom in, it cleared Earth. And it's going back around. Do y'all see that? But then, what happened the next time it came around? It hit us. Does everybody see that? Any questions? So the first time it went around, it cleared us. But the second time that it went around, we got hit. So we got hit right here. Now, you want to see something so cool that Desmos does? I thought it was so cool. So here's my graph on Desmos. You can clearly see that. If you come over here, and come to graph settings, this is the grid. If you come over here and change the grid to a circular one, a polar graph, look what it does. It's so cool. So not only can you see the X and Y axis, but now you can see the angles. You see them? Oh, shoot.
Yeah, that's pretty cool.
Isn't that cool? I was like, oh my gosh. And this is totally
on my calculator, the satellite never hits Earth in 3 pi radius, or 3 pi.
I would check because mine did, and I have a TI-83. Check over your equation again. 4 minus cosine of theta, 0 to 3 pi.
Let's see.
Why is that my green one? Oh, I just did the same one over again. Sorry. So let me do, what was it? R equals 3,960.
Yes, ma'am.
Okay. So there's the Earth and there's the satellite's orbit. So as you can see, you are going to, let me see if I can get a better window. So you can see, here we go. You can see that the angle, I mean, where it meets is about right here. Do you guys see that? So what angle is that? Do y'all see the angle?
2 pi thirds.
Very close. Anybody know what angle that is?
You went around twice, so you had to.
I did.
Got you. So it'd be 4 pi thirds.
I don't know. I'm going to add 2 pi to this. So that would be 6 pi over 3.
Oh, I did.
So that
2
would be
times 2 pi plus 3. I didn't add my.
8 pi thirds.
Yep.
Is everybody okay with that? How we got the 8 pi thirds? I agree that we ended at 2 pi thirds, but remember, there was a whole rotation before we got here. So it's the full 2 pi rotation plus another 2 pi thirds. So part B says, find the value of theta at the moment the satellite crashes to the Earth. So it's asking for the angle. So the angle would be 8 pi thirds. Cool, huh? I was like super excited about that. All right, so that's that one. And then remember, I wanted to add an example to this problem. And the reason why is because you can't forget what I taught you. You can't forget what you learned before. Unfortunately, I will give you the hard thing about math is you have to remember the stuff that we learned before because math builds, right? So here we go. Let's say I wanted you to sketch, because now we can sketch. I wanted you to sketch theta equals 5 pi over 6. Let's say that I wanted you to sketch that. I don't even know if you can do that on decimals. Or if you can do it on your calculator. Let me try. Theta equals pi over 6. Enter. Nope, it won't do it. See, I don't know. I don't know how to sketch that on a calculator is the problem. Nope, it doesn't do it. Okay, so I didn't know. I was like, I have no idea how to sketch this on a calculator. Like, I don't know how to put it into my TI 8384 Casio calculator, but it wanted me to sketch this. So I'm thinking to myself, I don't know where to start. So then I was thinking, well, let me try to change this into a rectangular format, because I don't know where to go from here. So if I wanted to change this into a rectangular equation, this is an example that I'm adding. If I wanted to change this into a rectangular equation, do you agree that tangent of theta equals y over x? Do we agree with that? SOHCAHTOA? Yes, no, Larry?
Yep. Yes,
Okay.
ma'am.
Dr. Chris Ely, what? How come you didn't use cosine? Because cosine would be x over r. And remember, we're trying to get rid of theta and r's, right? You either want to be all polar or all rectangular. So I wouldn't use cosine because cosine is x over r. I'm making it more polar, right? So then if you come over here, I'm going to replace theta because I know what theta is. Theta is 5 pi over 6. So I get 5 pi over 6 equals y over x. What is tangent of 5 pi over 6? Oh, I know. It's negative the square root of 3 over 3. It's on the unit circle. So now there's no trig. There's no theta. There's no r. Can't I get this to be y equals? Sure. I would have y equals negative square root of 3 over 3 x. Hey, I know how to graph that. How do I graph that? Anybody?
Just plug it into your calculator,
Sure.
but you have to go to the rectangular or
You
the
would have to go to rectangular form, but
rectangle.
what is this? What kind of graph is this?
The square. Oh, quadratic.
Nope, there's no x squared.
Oh no.
It's a line. Y equals mx plus b is a line with a slope of negative square root of 3 over 3. It's a line that goes through the point 0, 0. So now I can graph it. Because I think the question is just to sketch it, but your calculator won't sketch that. So you have to change it into a rectangular form so that you knew how to sketch it. And this makes sense because where is 5 pi over 6? On the unit circle, isn't 5 pi over 6 over here? Make sense? So then it's just a line that continued on. I wanted to add that. Make sure you have that down because I think there's one like that on your homework. And that's where we'll stop for today. So we finished 8-2. Okay? So we'll continue on with this again next week. You don't have a due date this weekend. So all you have to worry about is the test. When is the test due?
Tomorrow.
Saturday.
Oh, it's Saturday?
I'm
I
not.
thought it was the 17th.
Okay.
Or was it the 19th?
I think it's the 19th. So
Yeah,
make sure to study, get the test done, and then keep working on Chapter 8 homework, and we'll keep continuing on with Chapter 8 next week. Okay? Have a good weekend.
Thank you. See you.